In this video we're going to go over the method of partial fractions. So consider that you have a rational function. A rational function is something of the shape p over q, where both p and q are going to be polynomials. So it's possible that you express f as a sum of simple fraction or simple polynomials, provided that the degree of p is going to be less than the degree of q. So we need the degree of the bottom to be bigger than the degree of the top. Such rational function is going to be called proper. Now, the reason why with polynomials we can do that is because, remember, for a polynomial that is from the shape an x to the n minus 1, x to the n minus 1, plus 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 a1x plus a0, we can think of this, especially if the first coefficient is not zero, that this polynomial is from degree n. And if the f is improper, then the degree of p will be superior to the degree of q. And so we're going to have to do a preliminary step of dividing q into p by long division, until we have a remainder such that the degree of r is less than the degree of q. So something like this. We divide f by q, and so this is like dividing p by q, and dividing p by q is going to give me an amount s, and I'm going to have a remainder of this division. And so essentially I can do f divided by q equals s of x plus rx q, where s and r are also going to be polynomials. Sometimes our partial fraction exploration is going to end there because we won't need anything else. So let's see an example of that happening. So let's have the integral of x to q plus x divided x minus 1. Notice that in this case the numerator polynomial has a degree higher than the denominator. So let's go here to the board and consider what the integral of x cubed plus x over x minus 1 dx is. First than anything, then we're going to reorder this. We're going to do long division between x cubed plus x divided x minus 1. And remember that we're doing long division, but essentially what's going to happen is that once that we do this long division, then we're going to have that this is x squared plus x plus 2, and then we're going to have a remainder of 2, right, over x minus 1. And if you don't remember what long division is, remember what we're doing is we're dividing x cubed plus x into I believe this. We're dividing this by x minus 1, and then so what happens is that we're gonna get, I believe this is how you arrange it. We're gonna get this, and we're gonna get a final remainder of 2. But I'll leave the details of the long division to you. So now, if we have that the division of the two fractions is like this, then of course the integral x cubed plus x over x minus 1 would be this integral here. And this is mostly a simple fraction in a log. So we have x cubed over 3 plus x squared over 2 plus 2x plus twice log of x minus 1 plus c. So as you can see, rearranging this is much more effective for doing the integration than just keeping it in this way. But this is the case where the fraction is not proper. So we have that the numerator has a higher degree than the denominator. Notice that at the end, sometimes we'll have to do this. Notice that at the end we do have a proper fraction. The part that we get where this is the remainder over the quotient is a proper fraction. So this is a step that sometimes we do. Again, this is long division. So for doing long division, P over Q, remember what happens is that you take P and you're trying to divide it by Q, I believe. It's in this order. And so you get certain amount S of x, and you get a remainder of x. And so the proof of the division says that P is equals to Q times S Q of x times S of x plus R of x, which is the remainder. But then we divide by Q, then we get this bar. Okay, so this is the process of the long division that we're making. Okay? Please make sure to review long division if you still having trouble recognizing what this is. Now let's come back to the general notion of partial fraction. So now let's consider that we have P of x over Q of x, and that indeed the degree of P is going to be less than the degree of Q. Then we're going to be able to do partial fractions in one of the following cases. The first is the denominator Q is a product of distinct linear factors. The case 2 is that Q is going to be a product of linear factors. Some of them are going to be repeated. The case 3 is that Q contains an irreducible quadratic factor. None of those will be repeated. And the case 4 is that Q of x in the decomposition has repeated irreducible quadratic factors. So you might be wondering, well, what is this about the decomposition of Q? Well, by the fundamental algebra theorem, we have that any polynomial can be decomposed as a product of their roots. So it's going to be composed like x minus r1, x minus r2, assuming this is a polynomial of degree n, x over x minus rn. Okay? And this is assuming that all the roots are real roots. Okay? But you can also have some of these roots to be complex. And so those complex roots are going to give me irreducible terms. That's what we call an irreducible term. So one big example of an irreducible term is the x squared plus 1 polynomial, because when we're trying to get equals 0, then this is going to give me a square equals a negative, and so of course the solution will be plus or minus the complex number I, where I is the square root of minus 1. So anything that produces complex roots, or any polynomial of the way ax squared plus bx plus c, where b squared minus 4ac is less than 0, then will be an irreducible factor. Okay? Alright, but for now, let's see what happens when we have a nice decomposition. So let's see the first case. The denominator Q is a product of distinct linear factors. So in this case, Q of x is a product of distinct linear factors, and we can write Q of x equals to a1 of x plus b1 times a2 of x plus b2 times a3 of x plus b3 times and x plus bn. And none of these factors is going to be repeated. So if we can have Q in that decomposition, then we can write the ratio P over Q, we can write it as a constant over a1x1 plus b1, a1x plus b1, plus a2 over a2 small x plus b2, plus a3 over a3x plus b3, plus. And you can see we're essentially writing this big fraction as the sum of a bunch of other fractions that are gonna be much more easier to manage under integration. So that's the purpose of this. Now let's see some examples of this in use. So we're gonna see the two following examples that are gonna help me out define what the partial fraction is in here. So first we're gonna work with 1 minus x squared, 1 over 1 minus x squared. And so this can be rearranged as 1 over, and this is a difference of a square, so this is 1 minus x, 1 plus x. So it kind of holds the conditions that the denominator can be factored into linear terms that are not repeated. Okay? So by partial fraction, I know then this part can be then arranged as this: a over 1 minus x plus b over 1 plus x. Of course, this is what we call an identity. So this means that this is true regardless of the x that we're using. So because this is regardless of the x that we're using, we should actually use some x to try and find out who a and b are. So what I'm going to do first is, because I want to know who a and b are, then I'm just going to multiply by 1 minus x, 1 plus x up and down on both sides. So that's going to give me 1 is equals a, and then 1 minus x, 1 plus x over 1 minus x, and then plus b, 1 minus x, 1 plus x over 1 plus x. And so as you can see, I can cancel similar terms, and I'm going to get that 1 is equals to a 1 plus x plus b 1 minus x. So the easiest way for me to find a and b is to give some values of x that eliminate one of the other unknowns. So for example, I'm going to use x equals minus 1. And recall again that I can use any x that I want to, because this is an identity and this is true for any value of x. So if I use x equals minus 1, then this is 1 is equals to 0, because 1 minus 1, 0, so this disappear. And this becomes b times 1 minus minus 1, so 2. So I have 1 is equals to b, and that implies that b is equals 1/2. Now I can do the same to find out a. Now I'm going to do x equals 1. And if x equals 1, then I get 1 is equals to a plus 0, right? And so a is equals 1/2 as well. And so by conclusion, this is saying, hey, 1 over 1 minus x, 1 plus x can be seen as 1/2 over 1 minus x plus 1/2 1 plus x. And so this, as you can see, this makes so much more easier the integration here, because then I transform this into 1/2 1 minus x dx plus 1/2 1 minus 1 plus x dx. And this is going to simply be 1/2. And so because I'm going to get the substitution, u is equals 1 minus x, the u is minus 1, And so there's a minus 1 that is going to pop up over here. And this is going to be log of absolute value of 1 minus x. And then over here we don't have that issue. And then we got 1/2 of log of 1 plus x plus c. But we're using substitution to get to this result. Okay? So this is a basic example of partial fraction. We got to state the polynomial. We factor out the denominator to have all those multiple factors. Then we state how the fraction is supposed to be at the end. We need to find the constants, and then after finding the constant, then we get to integrate again and find the result. Okay, let's do one more example. So now let's go for this second one here. So we have integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx. So this one is a little bit more complex, as you can see, because you need to start factoring. We don't have the factorization from before, but is essentially the same thing. So we do partial fractions, and so for now I'm going to use PF as representation of partial fractions, and I can write this out as x squared plus 2x minus 1, and then I'm going to factor out the bottom. Notice that I can factor out an x initially, and so if I factor out an x, I get 2x squared plus 3x minus 2. Okay, but now I can factor this out as well. And this is going to be x times 2x minus 1, x plus 2. The process of factoring is something that you gotta review to make sure that you know how to factor this thing. I'm not gonna stop in that process, so make sure that if you don't know how to do this factorization, you review your algebra and you're capable of factoring out. Okay, so according to partial fractions, this is a over x plus b over 2x minus 1 plus c over x plus 2. Notice that before in the previous example we only have 2 constants, and now in this case we're going to have 3. But we can extend this by as many constants as we need. Now we want to do the same thing, so this is equals to this. This part is equals to this by identity. And so we can use any x that we want. So let's rearrange this so we can find out values. 2x squared, x squared plus 2x minus 1 is going to be equals to a. And so if I multiply this to the other side, here the x is going to be canceled, and I'm going to only have 2x minus 1, x plus 2. And for the b, I'm going to have x and x plus 2. And then for the c, I'm going to have x to x minus 1. Notice that because this is already factored, I can pick as the x, I always can pick the roots, because the roots will cancel all the other factors, and I'm going to be very quickly able to find the constants. So notice that the roots of these factors are 0, 1/2, and minus 2. So those are going to be the x that I'm going to use. So if x is equal to 0, I have minus 1. And so this disappears b and c, and I'm only going to have this one. So this is going to be a times minus 1 times 2. So minus 2. So this implies that a is going to be 1/2 positive. Same thing for if I do x equals minus 2, then this goes away, and now I'm only going to have c. And of course this side. So this side will be minus 2 squared plus 2 times minus 2 plus minus 1 equals to, and in here I'm only going to have c, so it's like c times minus 2, and then minus 4 minus 1 minus 5. And so this is here minus 2 squared is 4, minus 4 is 0, so I'll get a minus 1 here. And here I'm going to have a 10, so 10c. So this implies that c is minus 1 over 10. Okay. All right, so now let's find b. For finding b, I do the same procedure, but I'm going to use x equals 1/2. And so if I do this procedure again, I'll do exactly the same thing that I'm doing here, and I'm going to get that b is going to be 1/5. I'm going to skip the calculation, but please make sure that if you want to check the calculation, plug 1/2 in here and add the fractions, and then plug 1/2 in here and find out how I obtain that value. Now, but getting to the end, then this means that the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x then can be represented as a sum of different integrals. It's going to be 1/2 1 over x plus 1/5 1 over 2x minus 1, and then plus, or actually minus, minus 1/10 1 over x plus 2. Okay, and so now if I integrate that, I'm going to get 1/2 of log of absolute value of x plus 1/5, or actually, because the substitution, when I use the substitution u equals 2x minus 1, I'm going to get another 1/2 here multiplying, and the log of 2x minus 1, and then minus 1/10 log of absolute value of x plus 2 plus a constant at the end. Okay. So this pretty much will be how do we solve this. So in the next video, we're going to see the other cases of how I approach this if I have repeated terms or if I have reducible terms.